Hello everyone and welcome back to another mini concept, this time about solving for enthalpy change using bond energy and enthalpy of formation. This is the second to the last topic on enthalpy because there's still one more way to solve for enthalpy change. However, that one requires its own video. So first, let's have a quick recap. What is enthalpy? So enthalpy or enthalpy change is the quantification of the flow or change of heat energy within a system, or just in general energy of a system. When energy is absorbed by the system, we have a positive enthalpy change, and this is endothermic. And when we have a loss of energy from the system, that's negative enthalpy, and that's exothermic. Now, how do we solve for enthalpy when we're not given just straight up, oh, the enthalpy of the reaction is 2? Well, obviously it won't be 2, but like, you guys get the idea. There's two common ways, and these ways are actually what the last method circulates itself around. Now, first is bond energy. Okay, so what is bond energy? Every compound, okay, let's say we have methane. So methane, let's make this carbon here. Methane is given by CH4. So CH4 is structurally written as this. So there's single bonds all around, H, 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 and H, and each of these bonds, right? Each of these bonds, they require a certain amount of energy to break. That same amount of energy needed to break is also what is needed to form these bonds. Now, if you recall from the last video, endothermic is bond breakage. So this is break. While exothermic is forming. So this is, hold on. Let me find a better color. Here, form. So if we want to break these bonds, we need to have an endothermic reaction, because we want to add energy to the system to break these bonds. If we want to reform these bonds, let's say that we have free hydrogens in a reaction. If we want to make these bonds come back, we need to release energy, or rather we need to release energy after the bonds are formed. So there, and energy is released. So that's essentially the gist of bond energy. Bond energy is used to describe enthalpy because these energies are what changes in the system, or rather in the system, whenever there's a reaction. Because sometimes we can have bond breakage and other times we can have bond synthesis. So that's essentially the central topic of bond energy, enthalpy. So now, how do we use bond energy to solve for enthalpy? Well, the first step is by understanding the formula. So the formula is already given above. The formula for solving for the enthalpy of a system or a reaction, given the bond energy, is to have the summation of the bond energies of the reactants, and that's subtracted to and then we minus the summation of the bond energy of the products. What does that look like? Imagine this set of reactions. Okay, so let's write down this reaction, HHFF to HF. So this is H2 plus F2 turns into 2HF. So each of these have a structure that looks like this. So the structure is HH, so that's a single bond. This one is FF, single bond again, and this one is HF and HF as well. Okay, and how do we know if this is right? Well, we just want to check if there's a complete octet, right? And well, these do have complete octets. So now let's count the bonds present. So each of these bonds are different, okay? That's important to note. This single bond shared between the hydrogens are not the same as the single bonds shared by the two fluorines and the two hydrofluorides. So these all have different bond energies, and as you can see here, it's given. So this bond energy is 436 kilojoules. This one is 158 kilojoules, and this one is 565 kilojoules. Now these are all per bond. Okay, so every time that we see these bonds happen, this is the bond energy required to either form or destroy them. And these are standardized values. Okay, these are tabulated in books, chemistry textbooks, and online you can search for them if you have any particular reaction you want to try to solve. But for now, these are the bond energies that we're concerned with. So now let's try to understand how we would use our formula. Okay, so our formula says that we have to sum up the bond energies of the reactants and the bond energies of our products. So first, let's sum up our reactants. So on our reactant side, that's this side over here with the hydrogen gas and the fluorine gas. Now we have 436 kilojoules per bond of hydrogen, per single bond of two hydrogens. Now, how many of that do we have here? It says here that there's only one hydrogen. So since we only have one, that's 1 times 436 kilojoules, or rather just 436. Now for the next one, we only have one set of fluorine, which is sharing a single bond, and that's 158 kilojoules. And then we subtract the summation of the bond energies of the products. Now, how many from the hydrofluorides, how many single bonds are there in the reaction? So there are 2 moles of hydrofluoride, and both of them share single bonds. And for each single bond of hydrofluoride, there's 565. They possess 565 kilojoules of energy. So since there are 2 bonds, we multiply 2 by its bond energy, which is 565. Now, doing this on our calculator, we have 436 plus 158 minus 2 times 565, and this would get us an answer of negative 536 kilojoules. So what is the enthalpy of this reaction? Well, the enthalpy of the reaction of hydrogen gas and fluorine gas would result in an overall enthalpy change of negative 536 kilojoules. And this can be kilojoules per mole as well for the reaction. So this is the reaction there. So we can also conclude that this reaction is exothermic. And just like how we explained it in the last video, we can see that there was a synthesis reaction, so we expected it to be exothermic. Now, how about the next topic, enthalpy of formation? Let's move here. Now, this one seems a bit harder. Well, particularly because we're lacking numbers. We only have one set of numbers here, and it's this, whatever this is, right? But basically, how we solve for enthalpy when we don't have the bond energies is the enthalpy of formation of different compounds and elements. So now, elements can exist naturally, or they can have a standard state. So examples of these elements are hydrogen gas. So hydrogen doesn't exist by itself. In nature, hydrogen isn't just H, rather it always exists in pairs, H2. This is what we call a diatomic atom. Oops. Or rather, not diatomic atom, diatomic molecule. Now, other examples are oxygen, fluorine, what else? Chlorine, carbon here, carbon in the solid state, which is graphite, and a lot more. Oh, and nitrogen. Nitrogen exists in pairs as well. And this is, of course, the most abundant gas in our atmosphere. So that's important to take note of. But anyway, these exceptions, or rather not exceptions, these types of molecules are exceptions to having standard enthalpy of formation, or just in general enthalpy of formation. Why? Because these are their standard states of appearance. They don't need to have more, or they don't need energy to be created, because that's how they exist. And if we have these atoms, or these diatomic molecules, or just in general these standard state elements or compounds exist in a different state, let's say instead of hydrogen gas existing in gaseous form, we had it exist in liquid, this is no longer in standard state. So what is standard state? This is in standard state, but this is not. Right? So let's try to identify here which elements are in standard state. So first, like I mentioned earlier, carbon in the solid form is in fact a standard state element. Now how about hydrogen gas? Hydrogen gas is standard state. And oxygen gas is also standard state. Now, like I mentioned earlier, these don't need energy to be formed. So if there's no energy needed to be formed, there's no change in energy, which is also the enthalpy. So what is the enthalpy change for all of these three elements? Or yeah, these three elements. Well, these two diatomic molecules, but what's the enthalpy change for them? The enthalpy change is a stunning 0. So for every mole of these standard state elements, they actually need 0 kilojoules of energy. Now how about this compound? Well, compounds need to be formed. Compounds don't just exist, right? And that's our first giveaway whenever we're looking at an equation. So let's say that we have carbon dioxide, and this turns into, well, let's say that they split, so this becomes plus O2. Well, here this is obviously not going to be in standard state because carbon dioxide needs to form from these two these two atoms rather. So if it's a compound, typically it's not in standard state. And if it's in this form, depending on the state or the phase of matter that it's in, it can be in standard state. But of course, you're going to need to double check that using different resources. So now, what is the formula for enthalpy of formation? So I'll bring this over here. The enthalpy of formation for the formula for enthalpy of formation, I mean, is, just forget about that one. The enthalpy of formation of the products minus the enthalpy of formation of the reactants. So our product here is CH3CO2H, and the enthalpy of formation for that is negative 484.3 kilojoules per mole. So that means we only have 1 mole here, we only have to multiply this once. So that's negative 482. Let's use a different pen. Negative 484.3 minus 0. Because again, no matter how many moles we have, it's still 0 kilojoules per mole. So we're subtracting nothing. So that means our overall enthalpy change, or the enthalpy of formation for this reaction, is going to be negative 484.3 kilojoules per mole. Now, during exams, you have to be careful of the unit that's presented. Because sometimes, for example, when these aren't in standard state and you have different values there, sometimes maybe they will make sure that the teachers will make sure to try and trick you and put it in joules per mole rather than kilojoules per mole, while the other side is in kilojoules. And how do we convert? Well, it's easy to remember. For every kilojoule, that's kilogram. For every kilojoule, there is 1,000 joules. So if you want to convert joules to kilojoules, all you have to do is multiply the joules by this conversion factor. And if you want to convert kilojoules to joules, well, just flip it around. Okay, so that's the easiest way to do this. Now we'll have a bit of a level up and use some Gen Chem 1 concepts to solve for the next one. Okay, so let's bring this down. Okay, so GenChem 1 here will be used just really simply, no? Um it will just be multiplying the amount of moles by the enthalpy of formation. Okay, so again, we're following this formula, so let's write down our enthalpies. It says here that these are the enthalpies for these elements, or these the substituents of the reaction respectively. So our products are carbon dioxide and water, so we'll write them down first. Okay, so it says here that carbon dioxide has an enthalpy of formation of negative 393.5, and that's multiplied by nothing, so we're going to add that to the next product, which is water, which has an enthalpy of formation of negative 286 kilojoules. So that's negative 286 kilojoules. But hold on, there's 2 moles of water in this reaction, so that means we have to multiply this by 2. Now, how about our reactants? Our reactants are methane, and we also have oxygen gas. Okay, so methane exists by itself here in this reaction, as in it only has 1 mole, so its enthalpy is 74.8 kilojoules. Oops, I won't put that anymore. And then we add it to 2 moles of oxygen gas, which is in standard state, so it's just 2 times 0, or just in general 0, so we can just leave this at that. And our enthalpy change would thus be, or rather our enthalpy of formation would be negative 393.5 plus negative 286 times 2, done, minus 74.8. This would give us an enthalpy of formation for the reaction, okay, or the enthalpy change of the reaction, hold on, to be negative 1040.3 kilojoules. And we can also put this as per mole, but rather for now it's just kilojoules. Okay, so let's review for a bit before we move forward. So this is bond energy. We use the bond energies of the individual bonds within the elements or the substituents of the reaction to solve for the enthalpy. And this type of solving for enthalpy, we use the enthalpy of formation, and we use products minus reactants. Now let's try leveling up even more with GenChem 1 topics. So here we have more stoichiometry involved, and if we recall, stoichiometry is essentially just manipulating, or not exactly manipulating, but rather identifying the amount of substances involved during a reaction. Now, it says here in our question, well, I left the answer here so that you guys can be guided to see if you can solve it before I can, but it says here in the question that how much heat is produced by combustion of 125 grams of methanol under standard state conditions. So how much heat is produced, that's essentially enthalpy, right? And methanol is CH3OH, and we're going to combust it. Now, what is a combustion reaction? Combustion reaction is, to recall GenChem 1, it's when any element or compound is exposed to oxygen and it produces incomplete combustion. It produces carbon dioxide and water. In standard state conditions, so we have to apply the states of matter involved. So this is this is in gaseous form. This is in liquid form. This is in gaseous form, and this is in liquid form. Okay, it's important to note that in normal combustion, water is produced in the form of water vapor. Now, why in this case is it in liquid form? It's because in standard state conditions, it's typically dictated that it exists at room temp or 25 degrees Celsius. And at 25 degrees Celsius, our water is not frozen nor water vapor, it's liquid. So that's how we use it here. Now, before we move forward, we have to balance this equation. Because this is just a combustion reaction, but it's not balanced. So you need to make sure that the coefficients are right so that our enthalpies of formation, once we use them, they're not going to give us the wrong answer. Alright, so here, I've already balanced it prior to this video so that we can skip over that, right? But the balance coefficients are 1, 3 halves, 1, and 2. So basically, to reread the chemical equation, we have 1 mole of methanol reacts with 3 half moles of oxygen gas to form 1 mole of carbon dioxide and 2 moles of liquid water. Now, how much heat is produced by the combustion of this reaction when there's 125 grams of methanol? Well, first, let's identify what the enthalpy of this the enthalpy of this reaction is in the first place. The enthalpy per mole. Okay, so I don't have the table here right now, but I have the enthalpies of formation for each of these elements. So the enthalpy of formation, you can look it up. The enthalpy of formation for methanol is 239.2 kilojoules per mole. Oxygen gas is in standard state, so this is 0. Carbon dioxide is negative 393.5 kilojoules per mole. And liquid water is negative 285.8 kilojoules per mole. Oops, there. So now, to get the enthalpy of this reaction per mole, all we have to do is follow our formula. So we have negative 285.8 times 2 plus negative 393.5. Okay, there. Then we subtract our reactants, which is minus negative, so it's just plus 239.2. This will get us an answer of excuse me. This will get us an answer of negative 725.9 kilojoules per mole. Okay, so now for every ratio of these elements, essentially, like, let's say we produce 1 mole of carbon dioxide from this reaction, it will release negative 725.9 kilojoules of energy. If I produce 2 moles of carbon dioxide from this reaction, we'll just double our enthalpy. So this is our enthalpy. Alright, now, how do we solve for the heat produced when we have 125 grams of methanol? Well, now it's a bit, we have to understand, like, how does that work? How do we make sure that the ratio will remain the same? Because here it's given in moles, it does not show us grams. How do we make sure that we're going to get an answer that's in proportion with the enthalpy required for this reaction? Well, the way we do that is through stoichiometry. Now, I'll remove this part underneath. We'll only leave the enthalpy for this reaction. Okay, so let's recall how to convert mass to moles. First, we have to get the molar mass of methanol. The molar mass of carbon is 12.01. Oxygen is 16 and hydrogen is 1.01. So here we have 1 carbon, and then we have 1 oxygen, and we have 4 hydrogens. This will give us 28 plus 4.04, that's 32.0 01 there, 32.05 grams per mole of methanol. Alright, so how will we move forward from here? Now that we have the molar mass of methanol, we can determine how many moles of methanol are we actually dealing with here. So, hold on. Let's write this here. Molar mass of CH3OH. Okay. So, to get the grams to mole, we need to cancel out the grams. So we're just going to use our conversion factor. We'll have 125 times 1 mole over 32.05 grams. So essentially we're just dividing, and this would get us 3.9 moles of methanol. Alright, now where do we go from here? Well, okay, so we have 3.9 moles of methanol. But how do we know if this is what's more important to look at, or if it's the oxygen? In other words, which will be finished first? The methanol or the oxygen? Because obviously, if the methanol is going to be finished last, or if there's excess of this, then we have to be paying attention to how much oxygen is being used up, because that's going to limit our reaction. And that's why we need to figure out which one here is the limiting reactant. So how do we get the limiting reactant from here? Well, we know our moles of methanol. All we have to do is convert our moles of methanol to moles of oxygen, just to see which one here is going to be the limiting reactant. And to determine which one is which, we multiply it by the molar ratio, and whichever one has less moles, that is going to be our limiting reactant. So let's give that a try. Okay, so 3.9 moles of methanol, CH3OH, will be multiplied to our molar ratio. And our molar ratio always follows what we want over what we don't want. So here it's 1 mole of methanol, and we want oxygen gas, and the coefficient of oxygen gas is 3/2 moles of O2. And this will get us an answer of 5.85 moles. Now, we can see here that based on the numbers that we have, clearly our limiting reactant is going to be our methanol. So now we just have to multiply our methanol to our moles of methanol to our enthalpy per mole. So our final enthalpy would be 3.9 times our enthalpy for the reaction, and this will get us a final answer of 2831.01 kilojoules. Now the answers here are different, but that's because I use different sources for the enthalpies compared to this source. And decimal places also do really matter whenever you solve using different resources or different worksheets. So don't be too stressed whenever you notice that, oh no, my answer's 5 numbers away from what they had in the worksheet. If it's 5 numbers away, just double check your equations and check if you did them right properly, if you use the right values or not. But if the differences boil down to just the amount of decimal places you use throughout your solving, then just be confident in the fact that you know how to do it and get there in the first place. So yeah, that wraps up our discussion on enthalpy. I hope everyone learned something today from this video, and I'm going to cover the last topic on enthalpy in the next video, which is Hess's law. So before going on to Hess's law, I greatly encourage you guys to familiarize yourself with the concepts of enthalpy, or rather solving for enthalpy using bond energy and the enthalpy of formation, because that's really also the backbone of Hess's law. So again, thank you everyone, and I'll see you in the next video on the Hess's Law. Thank you and goodbye.